So we're going to give you a little talk about a radar we developed in-house. Very quickly, a little bit about me. I'm a Loughborough graduate back in 2002. I was sponsored through university by Celeritech with their design office in Lincoln. In 2002, I was a co-founder of Limwave Technology, which has grown greatly over the years. And in 2012, moved to Teledyne Defence and Space as a principal engineer. And I was the hardware system architect for the Phobos tactical threat warning system. In 2018, I founded Rathera. Our primary aim was to support both the design and development of integrated RF and electronic products with a real bent towards electronic warfare. So ESM, ECM, and electronic attack. And in 2003, I found myself as the chairman of the ARMS RF and Microwave Society. And so this presentation covers the design and development of a system for the characterization of the radar cross-section of uncrewed surface effect vehicles. Surface effect vehicles are also known as wing and ground effect. If you've ever heard of a Kranaplan or a Caspian Sea Monster, this aircraft uses the same aerodynamic effect. So the system consists of an X-band 4-watt PA LNA front end, a full block down converter up converter, coherent LO, wideband software-defined waveform synthesizer, a wireless electro-optics package, and also an ADS-B AIS airborne and marine receiver. So what's radar cross-section? It's a measure of how detectable an object is to a radar. Essentially, it's a unified figure, an equivalent area in meters, that if it was placed at the same distance as the target, would create an echo of equal power back at the receiver. And it's a product of the cross-section, the reflectivity, and the directivity. So just for reference, a person has a radar cross-section of about 1 meter square. You can see an insect there is sort of 30 dBSM down on that, so a factor of 1,000. Rather impressively, an F-22 Raptor has a smaller radar cross-section than an insect, which is thoroughly impressive, but it pays the price because it can't have an external weapons bay. And the cost of maintaining the wings and fuselage and all the joints is very, very expensive. So we were first tasked with doing some measurements on a scale model built from the same materials as the Finnish aircraft. And you can see the prototype on the right there. So we went to Unit 3 compliance in Bradford, used their anechoic chamber and reconfigured it basically as a compact range. A network analyzer we used in time domain with a couple of horns that operate over a wideband, a 1 meter parabolic reflector, and a turntable on which our model sits. So calibration of this is relatively straightforward. You can use a plate, you can use a corner reflector, but actually a polished sphere is a really good solution. As long as its radius is at least 1.5 times the wavelength, you'll get frequency independent RCS as a calibration figure, as it were. The key thing is to be operating in the optical region there. This sphere has a cross-section of about, or a radius of about 0.1 meters and a cross-section of about 0.03. So pretty small, but perfect for this application. So some quick results. I can't show you the numbers, but the key point here is to identify that we can pick out key features on this aircraft that are giving us a large return. Unsurprisingly, the nose, in particular the leading edge of the wings, and also the leading edge of the tailplane there. So, if we're designing a radar, we really ought to start out with the radar range equation, which is pretty much probably where everybody starts. This is a function of the transmitted power, the gain of the transmit and receive antennas, the wavelength we're operating at, and the expected target radar cross-section. And then S-min is our minimal detectable signal. So this is thermal noise and the minimum required SNR in our receiver. Atmospheric absorption isn't taken account of in that previous equation, but at X-band, where we're going to be operating, it's about 0.02 dBs. I think that's per kilometre, yes, so not a significant point here. So standard range resolution. So with an unmodulated pulse, the range resolution is entirely a function of the pulse length, tau in that equation. And so if you've got two targets that are sat within the same range extent such that their reflections overlap, you'll just get this sort of ambiguous bump in magnitude, and it's quite difficult, for example, to locate that second target. Now, one of the ways this is generally addressed is with pulse compression. Essentially what we're doing is increasing the bandwidth of the transmitted pulse. Linear FM is a really simple choice because it's easy to synthesize, and in that case the bandwidth is quite simply the difference between the start and stop frequencies. The wider the bandwidth, the greater the finer the range resolution. So if we take a compressed pulse and pass it through a pulse compressor, what we get are, in this case, two spikes that have got a significant improvement in range resolution and also a bump up in SNR, which is welcome. So when we compress a pulse in the frequency domain, and we'll come on to how we do that, what it produces in the time domain is a sync function. And we also see this root TB, where T is the uncompressed pulse width and B is the bandwidth. We also see an increase in SNR there as well. So this is a little bit of modelling in LabVIEW, just entirely synthesizing it. We've got an uncompressed chirp, which is the white trace, and then we take that same chirp and pass it through the compression algorithm. We get a big bump in SNR and a big improvement in range resolution. So in the analog days, as it were, this was done with a dispersive filter, matched filter. Essentially, the transmitted pulse would be swept. If it was a magnetron, that would be chirped. At the receiver, the received signal will be amplified and then passed through a match filter. And what that would do is it would delay different frequencies by different amounts. And essentially, it sort of crushes all that spectrum into one narrow unit of time. So essentially, the amount of energy is the same, and so the amount of power has to be increased for it to occupy the same extent. Now, we're in the digital days now, so digital signal processing is a thing. We could produce a matched filter perfectly in the digital domain, far better than, say, a SAW filter would have done in the analog days. But there are other methods as well, and one that works really well is an FFT. And so what we do here is our transmitted chirp that's been broadcast, we FFT it and store that in memory. And then as we're receiving blocks of received samples, we pass them through another FFT, multiply it by the FFT of our transmit chirp, pass it through an inverse FFT, and magically out the other side we've got a compressed pulse with improved SNR and improved range resolution. So we can modify our range resolution or our radar range equation to take account of pulse compression, and there's just a couple of extra factors we've added in there in green. This has been slightly modified, so we're now incorporating the thermal noise floor and also any of the digital signal processing and system losses, which is the LGES factor on the end there. So minimum blind range, this is an important one as well. We were doing measurements in a relatively constrained environment, and so it's quite important that we're able to measure targets at short ranges. That's primarily a function of the uncompressed pulse width and the turnaround time of our system. Turnaround time effectively is the time to turn our transmit pulse modulator into a high isolation state, to turn off the PA, to switch our TX-RX switch to the LNA path, to turn off a receive pulse modulator if there's one in there, and any settling times and propagation delays associated with all of those. So using our radar range equation, we can sort of refactor it to get RCS as the subject to the equation. And that's what we've done here. If we then do some further rearranging, we can get an equation which we see at the bottom there, which gives us corrected RCS based on the received packets, the range, and everything that's in the green brackets. Now, the important thing to note in there, the APCR factor is our calibrated pulse compression ratio. That's effectively a measure of our sphere at a distance over the calibrated value of our sphere over the measurement of that sphere using the system. Gives us a nice simple ratio we can use. If we factor that into our equation at the bottom there, we get something that's essentially fixed for a given pulse compression ratio. And what this means is that we can calculate RCS of any target at any point in our range continuously with very, very low processing overhead. So we did some predicted performance calculations. This table gives us 3 different pulse widths, some adjustments of the LFM bandwidth, linear modulation. And from this, we get an estimation of a minimum blind range of 45 meters, a maximum range of 2 kilometers, and a range resolution of 2 meters. So we've done some number crunching. Let's build a radar. So this is what we came up with. We have an X-band converter that sits in one chassis, and that has all the transmit and receive and block up down conversion electronics in it. We have a PXI chassis, which generates the TXIF and processes the receive IF. We have a computer that's going to do all of our real-time processing and the motion control electronics for the scanner that you see there. We also have a low latency, high resolution video link with a laser scanner and some telemetry, and all that's fed back into the system for processing. So the scanner, this is a 1.1 meter by 0.4 meter reflector. It's horizontal polarized, so for transmit and receive. There's a rotary waveguide joint in the base and also the azimuth and elevation servos. After we did some servicing on this, we got a 12 dB return loss from 9 to 9.7 gigs, so relatively wide operating bandwidth. So you may have guessed that this scanner was actually recycled, and it came off this helicopter. This is a Westland Sea King HAS-5 helicopter that was originally used for anti-submarine warfare. It last flew in 2015, and the scanner, as we see it, used to be located in that dorsal fin radome, highlighted by the green arrow. It'll be a theme you'll see from this presentation. Timothy Pelham at the University of Bristol did some modelling for me based on a load of measurements I did on this antenna, because we've got very little information on it. And he's developed a package called Lyceum EM, and this uses a ray tracing technique and an experimental meshing algorithm to do really fast measurements of large volumes of area where you've got arrays of antennas. And he was able to sort of crunch the numbers quite quickly when compared to CST, sort of hundreds of seconds versus many hours. There is a link in the presentation to get more information on this, but for those doing antenna modeling on platforms, it may well be an interesting solution. It's free, it's open source, Python. So having done some modeling, we thought it would be very useful if we could do some physical verification. If you just looked at the aperture of the antenna, you'd probably estimate that it had about 38 dBs of gain. When we looked through the literature on the Sea Searcher radar that this was used on the Sea King, that indicated about 34 dBs of gain. Our modelling showed a gain of about 27 dBi, so we're falling quite short. When we put this in the chamber and measured it, we found the peak gain to be about 27 dBi, so the modelling was absolutely spot on, which is impressive because that includes the feed horn as well. So this was quite a packaging exercise, getting all the block up down converter, the modulators, all the PA front end, the synthesizer and all the control electronics in there. Took quite some doing, but we got there in the end. So for the front end of this, we use a Qorvo QPM 1002 PA LNA. This part consists of a 4-watt PNA, an LNA, a TR switch, all in a 5x5 package, which is a very impressive level of integration. The front end design of this was taken from the Qorvo literature that's provided, and we also added a gas switch in there to improve TX and RX isolation. Now, we're going to have a bit of a segue as to how we manufacture prototype PCBs in-house, which some of you might find interesting. So all of the PCBs or RF PCBs used in this design were manufactured on 4350 Rogers, so 0.245 mil. And this was all done on our LPKF PCB milling machine, which is a fantastic tool. It allows us to do sort of fast prototyping of filters and distributed structures. It can isolation mill, it can drill the holes, it's brilliant. But there's one thing it doesn't do, and that's through-hole plating. Now, the processes used in commercial PCB manufacture are not really practical for a small business. And so we sought an alternative option. So prior to the fall of the USSR, a group of Russian chemists developed a technique whereby a compound could be used that would decompose at high temperatures into metallic nanoparticles of copper. And so this conductive layer covered all of the PCB surface and also the via walls as they'd been drilled. And so this is found to be very, very reliable on low aspect ratio holes, particularly thin PCB materials. And so the process starts by drilling your PCB or putting any slots in or any vias that you want installed, taking that PCB, dunking it in an activation solution, drying it off, putting it through an oven through that profile, and the copper decomposes over the full surface, over the via holes, over the slots, on all surfaces. Once that's done, quite simply, we put it into a conventional copper plating, electroplating bath with 2 anodes either side of the PCB. And in about half an hour, we can add 17 to 35 microns of copper over the full surface and all the via holes. Now, I will just make a mention of the activation solution. Most of those chemicals are really easy to come by, except the calcium hypophosphite. Now, unfortunately, this chemical has become unfortunately quite well known in that it's used in the production of illicit drugs. And so you can imagine its supply is quite well controlled now, but thankfully there is a small number of chemical suppliers that'll provide it in sort of 1 kilogram quantities. What I will say is, if you produce 500 mils of the activation solution, that'll pretty much last you a lifetime because the volume of material used each time is tiny. So the PCB is then put back on the milling machine and we do the isolation routing. And ta-da, we have a PCB with effectively as many vias as you want at no extra cost to you. And the great thing is that these vias provide good electrical and thermal conductivity, and they'll survive the repeated reflow of putting QFM parts down and taking them off again, which is really great, really. And impressively, this plating process only adds about an hour to the PCB manufacturing time. And so you can quite literally, within sort of a 2-3 hour period, go from nothing to fully plated PCB that you can put parts down onto. So the PA worked first time, which is always good news. It was actually driven slightly below saturation here, hence the slightly lower output power. The only thing we did come across is that the PA has a tendency to oscillate because, surprise, surprise, the TR switch sits on the front of here is reflective. And so when you look through the data sheet, sure enough, it says, yep, you've got to turn the PA off when you're not transmitting. Otherwise, you'll blind your own receiver. And that thing sounds like a relatively straightforward task, doesn't it? But what we're talking about here is a 25-volt drain supply that's really well decoupled. We need to switch that in 150 nanoseconds. That gives us about 170 volts per microsecond, which is going some. We can use a sort of a high current FET. The issue there is that conventionally they have quite high gate source capacitance, or CGS, and we must charge and discharge this quite quickly. We can't use a simple NPN bipolar driver as is shown in the corner there. We actually have to force current in and suck it out. And so Qorvo recommend using these high side gate drivers that would normally be driving these MOSFETs, for example, in a motor drive application. These work really well. They've got fast rise and fall times. The only downside is they've got quite long propagation delays, and so we have to take that into account in our timing. So when we first set this thing up and monitored the PA drain voltage, which is the green trace, it looked horrible. Unsurprisingly, this was the low frequency decoupling on the PA. We actually found we had enough local decoupling on the regulator that provided it, and so we could pull out, I think it was a microfarad capacitor. And then we got the green trace on the right there, which is lovely. Great pulse fidelity, lovely decay down to 0 volts, and fast as well. So as is the way with these depletion mode devices, we have to control the gate bias, and it has to be controlled over temperature. Qorvo, again, produced some quite nice application notes that use a PN junction as a temp sensor, and you can adjust the slope and offset on here just to trim and maintain constant drain current with temperature. There's also a TX-RX switch on this, as we've mentioned. The challenge here is we've got a switch between 0 and minus 28 volts fast. We decided to trade power dissipation for simplicity in this design. And what we use here is just some logic gates to create a complementary signal, Zener diodes to create an offset, and a couple of P-channel MOSFETs. And there's some hulking great big 1K 1 watt pull-down resistors that pull it down to the minus 28 volt rail. This works really well. It just gets rather hot. So the control circuits. Now, you remember I said that part was 5 by 5 millimeters. Well, all the electronics I've just described to you is occupied on that PCB. So whilst the part is tiny, you mustn't underestimate how much space is required for all the other control electronics. At the time of designing this board, we hadn't decided what the pulse width was going to be in the duty cycle. And so basically decided if some local charge storage was good, more charge storage was better. So the synthesizer used a Hittite Mimic VCO. This has effectively a ×2, a ×1, and a div2 output. That was used with an analog devices synthesizer IC. We actually lock the loop at 14 gigs and use the 1x output at 7 gigs to drive our LO amplifiers and out to our mixers. We did some basic modeling using analog devices tools. We estimated the phase noise at the ×2 output was going to be -75. At the divided out output, that's effectively at a quarter of the frequency. We would expect to see a 12 dB improvement and a figure of about -87 dBc per hertz at 10 kilohertz. And sure enough, that's exactly what we've got. So credit to Analog Devices for their modeling tools. So again, this was produced in-house and put on our standard jig with its various DC interfaces on it. And when it came to the pin pulse modulator, we saw no point in reinventing the wheel rather. We opted to essentially do some more recycling. This is a pin pulse modulator. I think it was out of an 8684 signal generator. I think that's what the model number was, but basically that signal generator is nearly as old as me. But these things still work and they're fast. They've got 80 dBs of isolation at the band of interest. And we used a MACOM MADR pin driver. These are great. It's an SO8 IC that is a complete driver for pin applications. Anybody that's had to deal with that will know often it involves quite a bit of circuitry to be able to switch bipolar voltages fast with very little latency. These chips are hard to beat in terms of price, real estate and performance, so that's what we use to drive it. So in terms of frequency conversion, it was dead simple. Essentially, we come in the 9 gigs band. We have an LO around 7 gigs, and that's tunable, and an IF of around 2.15 gigs. We've got some flexibility in both the LO and IF frequencies, so if there's any leakage in from, say, an LTE signal or a mobile phone signal, then we can tune away from that. So the band-defining filters, we actually used a triplexer for this function. We wanted to make sure the whole system covered a fairly wide band in case we wanted to configure it for another application, and so the 8 to 12 gigs port of the triplexer was used as our RF port, and the other 2 ports were terminated. And the good thing about that is it ensures that the mixer, all the mixing products are well terminated as well. And we have an IF filter in there that goes from about 0.5 to 4 gigs. As is the theme with this project, again, we were recycling parts, and these actually came out of the Racal Mir 2 Orange Crop ESM receiver that was fitted to that Lynx HAS-2 helicopter. The helicopter had been decommissioned at that point. I didn't just go and take it out. So timing's everything. There are several components that have to be accurately switched in sequence to maintain a high fidelity pulse. Our pulse modulator on the TX side, the isolation switch, our PA drain voltage, as we've said, the TX-RX switch, the RX pin modulator. Now, that would all have to be switched in sync with our chirp as well. And so developing all the circuits to deal with that would be quite an undertaking. Now, fortunately, the Aeroflex signal generator we use in this project, which is in a PXI chassis, you'll see that later in the presentation, has 32 bits of waveform memory, and I think it's something like 2 gigabytes deep. Essentially, the I and Q components are 14 bits each, and so that leaves 4 bits which are used as what are called waveform markers, and they can be used for various functions. But what we decided to do is route them out to our X-band microwave chassis and use that to switch the pulse modulators, the switches, and all the rest of it. The great thing is that's in perfect synchronicity with the waveform, and through adjustment of the timings that you see on the bottom there, we can get perfect pulse fidelity. And so doing some quick measurements of the generated pulse, in the bottom left, that's power versus time, so we've got a nice waveform there. And then top right-hand corner, frequency versus time, you can see we've got a nice linear sweep. So, motion control system. All of the electronics, again, for motion control are in a single chassis. The azimuth and elevation axis of the scanner use two-phase AC servos. Now, we couldn't find any information on these, and so experimentation basically allowed us to determine that they're driven by two sinusoids at 10 to 80 hertz and about 28 volts in magnitude. The interesting thing about these servos is effectively you drive them with two waveforms at full amplitude, and then just by adjusting the relative phase relationship, you can change the direction of rotation and also the torque that's applied. Now, the scanner that came off this helicopter used these Muirhead resolvers to provide continuous measurement of angle. They deliver accuracy in the orders of sort of hundredths of a degree of resolution, and they are fabulously expensive. The resolvers are excited with a simple sinusoid, and what they deliver are two sinusoids that, when processed, give you a continuous angle measurement. Fortunately, nowadays, there are digital chips that will take those two components and give you a digital readout of angle. So the rack system that you'll see on the exhibition space has our PXI chassis at the bottom with the transmit-receive modules in, a radar processor, essentially a PC running LabVIEW, and then a few other receivers and bits and pieces. So the IF generation and digitization are done with these two Aeroflex modules, one as a signal generator, one as a receiver. They both go up to 6 gigs, operate over a sort of 90 megs bandwidth, and have lots and lots of memory on board for waveform generation and for digitizing the received samples. So our radar processor computer does lots of things. It configures all the hardware, it synthesizes the chirp, transfers it up to the waveform generation box, also does all the receive processing signaling, and also does the tracking of the motion control system, as you'll see later. So here's just a couple of quick screenshots. This is the motion control. You can see there a plot of azimuth, of angle versus time. We can also monitor the health of all the various components in the system. All of the boxes that are up on the tripod are accessed over a single RS422 bus, so the cable can be quite long. We've got our TX waveform synthesis there. We can adjust the bandwidth of the chirp relative to the bandwidth of the system. There's also windowing functions we can apply to adjust the side lobes in the time domain, and various other functions we can adjust in terms of timing relative to that. So in terms of our receive processing, the plot that you see there on the top there with the white trace, that's effectively log amplitude versus time. And then on the trace below is the pulse compressed version of that with much more clearly defined reflections. On top of our scanner is a electro-optics package. So this is a zoom camera, laser rangefinder with a pointer. There's also a compass, a GPS receiver, and a few other bits and pieces. And they all feed their information into a piece of software called OpenHD. This is actually developed for use in drones and provides sort of super low latency, high resolution video over a 2.4 or 5 gigs Wi-Fi link. It's a really nice solution. So the data that comes out of our various sensors are packed together and then sent through something called the light telemetry protocol into the OpenHD software. And then that gets broadcast alongside our video feed. And so the electro-optics package is completely wireless with its own battery. We also added in an ADS-B receiver. We've not added AIS support yet. What this does is it'll receive the broadcasts from aircraft above a certain size that require to carry an ADS-B transponder. And that transponder is continuously transmitting latitude, longitude, and altitude. Well, if we know where the aircraft is and we know where the radar is, we can work out the azimuth and elevation of the radar necessary to track that aircraft, effectively cooperatively tracking it. And so this is the scanner operating about 20 meters above the river air on a balcony. All I can say is, what must our neighbors think? They really must wonder. So this is, unfortunately this video won't play, but this is a live view showing the time domain on the top there in the white trace, the pulse compressed version in the yellow trace, and then on the plot on the far right there, the intensity plot. As we sweep in angle, we can see the various targets being illuminated. So you might be wondering about licensing. We apply to Ofcom for an innovation and trials license. This permits you to transmit in a specified band under certain conditions. It allows fixed operation at one location for a 1-year period, and a non-operational license costs as little as £50 a year. It's really great for experimentation, and the application took about 10 to 12 weeks to get granted. Very easy process. So in terms of safety, nobody needs to worry. This thing's transmit about 3 watts peak. Even when you factor in the antenna gain and the wavelength, our duty cycle is no more than 10%. In general, it's a lot less than 1%. And so the field strength at 3 meters is way below any public and occupational limits there. So flight trials of the Uncrewed Surface Effect Vehicle, Elvington Airfield was selected. We were going to operate on the concrete hard stand you see there. That was originally modified at Elvington, or it was built at Elvington for the US to deploy their nuclear deterrent bombers in the 50s. In the end, they were never sent, and so it's remained unused. And so the first flight of this Uncrewed Surface Effect Vehicle, which you'll see in the middle there, I would describe as short and very distinguished. Having a solid surface like this is really great for taking off because it's very low drag compared to, say, taking off from water. The only downside is there's a much higher risk of what we'll call unplanned disassembly on landing. Unfortunately, there was no more testing with that craft after the first flight. And so when it came to using our radar, we were a bit disappointed, and so we were essentially left at just looking at the surrounding terrain. And so this is a capture of exactly that, and it's not the easiest to see, but we've actually got targets all the way out to about 4 kilometers that we can see there, and the full 360-degree rotation. If we take that data and plot it onto a Google Maps view of the same area, we can see the blind range in the middle where we get no return, and then as we move out from there we can see all the vegetation, some of the surrounding buildings, the forest down to the bottom there. You might be wondering why the buildings aren't picked up, but that forest was really dense, and so it was effectively shadowing all of those objects. We found we got good sensitivity, really good range resolution, and it's pretty impressive for only a 3-watt transmitter. Hopefully we'll get to return soon when they've put the aircraft back together. So a couple of quick credits. James Paulson at Unit 3 Compliance, thank you very much for the use of your anechoic chamber. Really great facility there up in Bradford, and also Timothy Pelham at the University of Bristol for his modelling and support along the way. So thank you very much. Any questions?